So we're going to start this video is on chapter 12. It is lecture 1 part 2. And in this particular video we're going to cover 4 ways to report a solution's concentration. Molarity should be expressed as a capital M. Molality should be expressed as a lowercase cursive m. Or maybe a better way to say it is italicized m. Okay. Mole fraction is an italicized x, so it should look like this. Okay. And of course you have percentage, which we all know what it looks like. For those of you who are following along and taking notes in a notebook, I think to get the most benefit, you shouldn't just copy down the calculation. You should get out your calculator and make sure you get the same numerical values as I do. Make sure you aren't making any mistakes in terms of using your calculator. And make sure you do use a notebook and write detailed notes, because with this semester there's going to be a lot of math, and so it just really does make sense to have detailed lecture notes so that you can refer to them when you're actually doing your homework and studying for exams. So there are 4 ways of expressing a solution's concentration, and really with the concentration it really is an expression of how much solute is divided by how much of the total solution you have. Okay. This is sometimes not always true, but for the most part, that's kind of the general idea. For molarity, you express it in terms of moles of solute over liters of solution. And remember, the solution here is the total, right? Because the solution is the solvent plus the solute. Okay, so liters of solution is the total amount. Mass percentage is the mass of the solute divided by the mass of the solution, and then you're going to multiply by 100 to get the percentage. And again, here it is the solution, so it is the total amount. Okay. Well, with mole fraction, it is moles of, and we have A. A here can stand for the solute or the solvent, depending on what you're calculating. Okay. Again, the denominator is total moles of solution, and again, this is the total amount. Okay. Now, the one concentration expression that is slightly different is molality. It is moles of solute over kilograms of solvent. Notice here, this is not the total. Okay. The solvent is, remember, is the larger component. Okay. Just keep that in mind. With all the other ones, it is the total amount, but with molality, it is kilograms of solvent. So remember, that's why I wrote here, it's very important to remember. The solution is not the solvent. The solution is the total amount. The solvent is the major component. All right, so let's just do an example here. It says here, molarity, we need to convert everything into moles and liters. Okay, so we need to convert everything into moles and liters, because what we know is that molarity, okay, and molarity, remember, is the capital M, is equal to moles of solute over liters of solution. Okay, and I will use SOLN as an abbreviation for solution. Okay, so it says here, if you have 2.5 grams of ethanol, okay, and it's added to a beaker, and then water is added until the total volume is 50 mils. Okay, what is the molarity? So let's write down what we know. Okay, and really we would like to know what is the moles of the ethanol, right? Because that's the solute. We're going to stick that in the top of our fraction there. And we do need to know the total volume or the liters of the solution. Okay, so if we write down what we know that we have 2.50 grams of ethanol, okay, and we know we need moles, so let's convert from grams to moles under the no, okay. So with that, we know that the molar mass is how we convert from grams to moles, and the molar mass of ethanol is 46.07, okay, and it is 1 mole, okay. This comes out to 0.0543 moles of ethanol. Okay. With the liters of the solution, we know the total volume of the solution is 50 mils, and just to convert from milliliters to liters, 1 liter is 10 to the third or 1,000 milliliters. So this comes out to 0.0500 liters. Okay, I like to do all the conversions underneath no, so that I am already in the units that I need to be to do the solve part. And to do the solve, really the molarity is equal to, and again I have the moles here and the liters here. Okay, so I'm just going to plug that in. 0.0543 moles of the ethanol over 0.0500 liters. So this comes out to 1.09 moles over liters. Okay, you can write it like that, or you can write it as 1.09 capital M, which stands for moles per liter. So this is the same thing as this in terms of what you write. Okay, do you want to put your final answer in a box? And you need to check your significant figures. You have 3 significant figures in your given, so you should have 3 significant figures here. All right. Molarity, that's the first kind of way we calculate a solution's concentration. Mass percent is mass of solute over mass of solution. So it says here, how would you prepare a 425 gram of an aqueous solution containing 2.40% by mass of the sodium acetate? So remember, 4.25 is your total mass of the solution. Okay, so really you're just plugging it into this equation. Here the mass of the solution is plugged in. You're solving for mass of solute. Think of this as your x. Okay, and really you're just going to divide both sides by 100 so that this cancels out. Okay, you're going to multiply by 425 so that this cancels out. And so you get the mass of the solute is 10.2 grams of sodium acetate. Now, if you went into lab and you added 10.2 grams of sodium acetate into a beaker and then added 425 mils of water, is this solution 2.4% by mass? It is not, okay? If you added 10.2 grams, then you added 425 mils of water, okay, and with water the density is 1, so that's the same thing as 425 grams of water, okay. You're not going to get 425 grams, you're going to get 435.2 grams of the solution, which is not what you want. And in addition, your percent mass would not be this, because you would do 10.2 divided by 435.2 and multiply that by 100, and it's not going to be equal to 2.4%. Okay? Remember, okay, that the total mass is 425. Okay? So this is wrong. Okay? What you need to do is you need to go 425 minus 10.2 grams. That will get you the amount of water that you need to add, or the amount of solvent that you need to add. So you need to add 414.8 grams of water. Okay, this is really important when you're doing stuff in lab on how to make solutions to make accurate concentrations. So the third kind of way to report concentration is called molality. Molality is moles of solute divided by kilograms of solvent. And so it's saying here glucose C6H12O6 is a sugar that occurs in fruits. It's also known as blood sugar because it is found in the blood. And so they're asking you what is the molality of the solution if it has 5.67 grams of glucose dissolved in 25.2 grams of water. Obviously, this is the solute because it is the smaller amount, and this is the solvent. Okay, so let's write down what we know. We would like to know moles of the solute, in this case, glucose. Okay, and we would like to know the kilograms of the solvent, in this case, water. Okay, so we need to do some conversions, and we're going to do it underneath no. 5.67 grams of glucose. Okay, and to convert from grams to moles is again the molar mass. So it's going to be grams of glucose to moles of glucose, and the molar mass of glucose is 180.16. Okay, this comes out to, if you do the calculation, 0.0315 moles of the glucose. Okay, we're going to need that when we calculate the solve. Okay, in terms of the kilograms of water, we do know that we have 25.2 grams, so let's go ahead and convert that to kilograms. 10 to the third grams, or 1,000 grams, is 1 kilogram. So this comes out to 0.0252 kilograms. Okay, now that we have the moles and the kilograms, we can solve. And again, molality, remember, is the curse of m, lowercase. This comes out to 0.0315 moles of glucose over 0.0252 kilograms, okay, which comes out to 1.25 moles per kilogram, okay, or you can write it as 1.25 curse of m, or molality, okay. Either of these expressions are correct, okay. At the last, we should check. We have 3 sig figs in both glucose and water reported, so we should have 3 sig figs. Mole fraction. Mole fraction is the last kind of concentration expression we're going to cover, and mole fraction is where everything is in moles, okay? So really, you just convert everything to moles, okay? So if you have 2.5 grams of ethanol, what do you know? You need to know the moles of ethanol, and you need to know the total molar amount. And they do tell you that the total volume is 50 mils of the solution. So you're going to go ahead and say 25 grams, convert it with the molar mass. This is the molar mass conversion factor, okay, to get the moles of ethanol. Then you're going to take 475 milliliters of water, assuming that the density is 1 gram to mil. You're going to convert from grams to milliliters to grams, from grams to moles using the molar mass of water, and you're going to get 2.64 moles of water, okay? And to find the mole fraction really is just the moles of ethanol over the total. And remember, the total is ethanol plus water, okay? And so you're going to get 0.0201 as your molar fraction. Notice there are no units for the molar fraction, okay? Because the moles and moles cancel out, okay? With this problem, we assume that the density was 1. The solution density was 1. It is not always 1 gram per mil. If it isn't, we will tell you in the problem what the density is. The density of a solution often depends on the various components, so that is something that would be given to you in the problem. Now, what you might also, the textbook might also ask you to find the mole fraction of the water instead of the ethanol. For this one, this is the mole fraction of the ethanol. Okay. If you wanted to find the mole fraction of the water, it's really easy. It's really just 1 subtract 0.0201. Or you could do, another way to do it is to say the moles of the water over the total, okay? And you can calculate that as well. You can do 2.64 over 0.0542 plus 2.64. And you're going to get the same answer here as you would get here. Okay. I'm not going to do that. You can always go ahead and try that, but it should get you the same thing because the mole fraction total should always equal 1, right? In terms if you have all of the components added together. Last but not least, a lot of times we would like to express the concentration in a different way than what is given. Let me just backtrack a little bit here. Okay, let's say that I express something in terms of molarity. Okay, if I took this and I said 2.50 grams of ethanol and 50 mils of water. Okay, and I got this as the molarity. Can I take this same solution and express its concentration in molality? Absolutely. That's what we did here on this slide here, right? Sorry, a mole fraction, right? We took the same amount, 2.50 grams of ethanol and 50 mils of water, and we expressed it as mole fraction. We can express a solution's concentration in any of these 4 ways. Okay, there's not like there's a wrong way or a right way. Okay, and so a lot of times, let's say you're reading something and it's in molarity, and you would like to have the concentration and mole fraction to compare to what you're doing. Okay, so there are ways to go and convert from each of these concentration expressions into other concentration expressions. So I actually, this is not from the book, this is something I put together just to make it a little bit easier because it does get a little bit confusing on how to do it. And so I use this little kind of table that I put together, or this figure, to help me to figure out how to convert from one to the other. Okay, and we're going to use this as we go along in this video. Okay, so let's say you need to convert from molality to mole fraction. Okay, so example 12.5 in your book says you have an aqueous solution of 0.12, and this is molality. This is the Kirchhoff M, so this is molality. Okay, or moles per kilogram. Okay, of the glucose. They want to know what are the mole fractions of each component. So they want to know what is the mole fraction of glucose, and they would like to know what is the mole fraction of the water. It is water as the solvent because it is an aqueous solution. So I think the best way to do is to refer back to here and say we're at molality, okay, and we would like to go to mole fraction. Okay, so how do we do that? We're going to follow both of these legs of our chart. We're going to go moles of solute, okay, and we're already in moles of solute. That's what we need, so we're going to keep that, okay. But we also need to follow this leg, and we're going to take the kilograms of solution. We're going to convert it to grams, okay, to get the mass of the solvent. Then we're going to use the molar mass to convert to moles of the solvent. And then we're going to add the moles of solute and moles of solvent to get the total moles to plug it into the denominator, okay. So really we're going to have to follow 2 pathways to get to mole fraction, okay. So first and foremost, 0.120 moles per kilogram really means that you have 0.120 moles of glucose in every 1 kilogram of water. Okay, and you do need moles of, in this case, you need moles of glucose. Okay, and you already have moles of glucose. The moles of the glucose is 0.120 moles. If you have 1 kilogram, and you can just assume you have 1 kilogram of water, okay, that's okay. Then you need to figure out the total moles. And to figure out the total moles, you do need the moles of water first. And then with the moles of water, you're going to add that to the moles of glucose to get the total moles. So again, you should follow this little chart. You're going to go from kilograms to grams, and then grams to moles, right? So let's do that. We're going to go 1.00 kilograms, okay, kilograms to grams, and then grams to moles. Okay, so 1 kilogram is 10 to the third grams for the metric system, and the molar mass of glucose is going to be molar mass of water, it's going to be 18, okay, 16 for the oxygen and 2 for the hydrogen. This comes out to 55.6 moles of the water. So therefore your total moles is going to be the addition of 0.120 plus 55.6, which comes out to 55.72 moles. Okay, so then you need to find the mole fraction of the glucose. This is the moles of the glucose, 0.120 divided by the total. This comes out to 0.00215. And again, mole fraction has no units. Mole fraction of the water is going to be equal to 55.6 divided by 55.72. This comes out to 0.998. Again, no units because it is mole fraction. Okay. All right. If you wanted to go from molality to molarity, okay, so you have an aqueous solution and it is 0.273. And this is again molality, is the curse of M. Okay. And they would like to know the molar concentration. Your book uses this phrase molar concentration to refer to molarity, or moles per liters of solution. Okay, so really, if you think about it, again, like we did before, 0.273 moles per kilogram really just means that you have 0.273 moles of KCl if you have 1 kilogram of water. Okay, so really, what do you know? You know that you need the moles of the KCl. You have that already, 0.273. Okay, you do need liters of solution, and right now you have liters of a solvent. Okay, so really I would go back to here and let's just look. We have molality, and we would like to go to molarity. Okay, so let's erase this red that I drew before. Okay, in this particular case, okay, we have the molality, so we already have the moles of solute, so that's good. Okay, but we need to go from kilograms of water, and we need to convert it to grams. Okay, then we need to add that, so we do need to convert this to grams as well with the molar mass. Why? Because we need to know the mass of the KCl. Okay, so we're going to add the mass of the KCl and the mass of the water to get the total mass of the solution. Okay, and then once you have the total mass of the solution, you're going to use the density to convert to milliliters or liters, and then you can plug it into your molarity expression. Okay, so we're going to follow that all the way through. Okay, so we have our 1.00 kilograms of water. We're going to convert from 1 kilogram to 10 to the third, or 1,000 grams. And then we're going to convert from, and that will get us the grams of the water, which is 1,000 grams of water. Okay. We would also like to know the mass of the KCl, so really it's 0.273 moles of KCl times the molar mass of KCl, which is 74.6. So this comes out to 20.4 grams of KCl. Okay, with these two amounts, if you add them up, okay, that will get you the total mass. So so that'll get you, if you add them up, 1020.4 grams of solution. Okay. But remember, you need liters of solution. So again, we're going to do one more conversion. We're going to convert from 1020.4 grams to liters. Okay, and they give us the density here. 1.011 times 10 to the third grams equals 1 liter. This comes out to 1.009 liters of solution. Okay, with that in hand, we can then solve. Okay, really the molarity is equal to the moles, 0.273 moles over the liters of solution, and this comes out to 0.271 moles per liter. I'm just going to write big M instead of moles per liter. Okay. Now if you compare this is the molarity. Okay. And this is a typo. This is the molality. 0.273 is the molality. Notice that these two numbers are fairly equal or very, very close to one another. 271, 273. The only difference is that last sig fig there. Okay. This is often the case that the molarity and the molality are used interchangeably when the solutions are very dilute. Okay. The reason being the liters of the solution versus the kilograms of the solvent. Okay, in this particular case, there's 1.009 liters of solution, and there's 1,000, okay, or 1,000 grams or 1 kilogram of solvent or water in this case, right? They're almost the same, right? The reason for this is because there is very little solute. Okay, when there is very little solute, the amount of solution in liters and the amount of solvent in kilograms is about the same, and so therefore the molarity and the molality are used interchangeably and about the same. All right, last but not least, let's say we wanted to convert from molarity to molality. So you have 0.907 capital M, or molarity. This is molarity of lead nitrate, and they would like to know what is the molality of the lead nitrate. Okay, so again, we should scroll back to our little table here. What we're going to do is exactly the opposite of what we just did. Okay, we're going to take our molarity and convert the 1 liter. Okay, we're going to convert it to the milliliters, and then milliliters to the grams using the density. Okay, so we're traveling in this direction. Okay, then we're going to add the grams of the water and the grams of the lead nitrate to get the mass of the solvent, and this is in grams. We convert that to kilograms to plug it into our molarity expression. Okay, so let's go ahead and do that. And again, we're just following this pathway. All right. So, if you have 0.97 moles per liter, you really have 0.907 moles of the lead nitrate in 1 liter of solution. Okay, so do we know what the moles of the solute, in this case the lead nitrate, is? Sure. It is 0.907 moles if you have 1 liter of solution. So we're going to convert our 1 liter of solution to milliliters, 10 to the third milliliters in a liter, and then we're going to go from milliliters to grams using the density. In this case, the density is given here as 1.252 grams per milliliter. This comes out to 1,252 grams of solution. Remember, this solution is the water plus the lead nitrate. Okay, this is not just the water. So you need to subtract the amount of the lead nitrate. Okay, so to do that, we're going to convert the moles of the lead nitrate to grams of the lead nitrate so that we have that amount. Lead nitrate is 331.2 grams per mole as the molar mass. This is 300 grams of the lead nitrate. Okay. Sorry, this should be 2. Okay. So to find the mass of the water really is the mass of the solution minus the mass of the lead nitrate. This comes out to, I'm going to write it here, 952 grams of the water. Okay, we do need the water to be in kilograms, so we're just going to convert that really fast. 952 grams divided by 1,000, 0.952 kilograms of my water. Okay, so really the mass of the water in kilograms is here. The moles of the lead nitrate is here. So let's solve. Okay, your molality is going to be 0.907 moles divided by 0.952 kilograms of water. This comes out to 0.953 moles per kilograms, or we can just write cursive M for molality. Okay, so really this is the idea of this video, is to be able to calculate either molarity, molality, mole fraction, or mass percent as the concentration. And the second main point in this video is to be able to convert from these concentration expressions. This is actually the main emphasis of Chapter 12, so this is really where the bulk of the calculations lie. After you watch this video, what I would suggest you do is to go ahead and open your homework booklet and to Chapter 12 and do these problems on the solution concentrations. All right, this ends this video, Lecture 1, Part 2, on reporting solution concentrations.